that I'm going to want to do, what is the very first thing I'm going to want to do if I would like to solve this system of equations? Brandon? Put it in a matrix. Exactly. It's the answer to everything in this class. And the matrix that we're going to use on this example, of course, this is what we call A sharp. Okay, so A sharp is just the matrix that we write down, and I just grab all of the coefficients from my system over there, 2, -3, 1, -1, 1, and 0, right? That's the first row. And then for the second row, we look at the second equation, 4, -6, 2, -3, -1, and -5. And then the third row is -2, 3, -2, 2, -1, and that's augmented with 3. The unknowns themselves do not show up in the matrix itself, but of course they are associated with the various columns in this A sharp matrix. So it's just good to kind of keep track of that. It should be written in the same order as well. Okay, so far so good? So I've got my A sharp. The next step is to use EROs. So I'm going to try to get this thing into row echelon form. Now remember that in the row echelon form, you have to have pivots, and the pivots have to be 1. I don't see any 1s over here on the left part of the matrix. I could create a 1 very easily if I just multiply the first row by 1/2. But if I was to do that, I would create a whole bunch of fractions across that entire first row, which are going to then sort of spread through the whole matrix in a way that is hard to do the calculations in our head. So I actually do not recommend turning this 2 into a 1 quite yet. Eventually, I'm going to multiply that first row by 1/2, but I'm not going to do it yet. I'm not going to do it yet. I'm going to leave it as a 2. I'm going to use this 2 to turn the 4 into a 0 and the -2 into a 0. Does everybody remember that the pivots have to go down and to the right? So I cannot have pivots underneath other pivots. So if I have a pivot that's going to be in that top left corner, everything below that pivot must be a 0. So to get that to happen, guys, can somebody tell me what ERO, if I leave the first row the same, what ERO can turn this 4 into a 0?
-4.
Say again?
-4.
Okay, it's got to be one of these things. I can permute 2 rows, I can multiply a row by a constant, or I can add a multiple of one row to another. Those are my EROs. Yes, please.
2 times row 1 minus row 2.
Okay, no minus. So it's permute, multiply, and add, but you're on the right track. What I want to do you want to tell me, Brandon? Okay, I could take, that would work. I could take A3, 2 of 2. I generally like to work top down. So it's not wrong what you told me, but just to get kind of good habits and consistent habits, I would prefer to use row 1 to help me work on row 2. And what's it going to be?
You multiply row 1 by -2, and then add it to 2.
Add is the key thing. It's adding from row 1 to row 2 of -2. So I'm going to take -2 times the first row and add it to the second row. Okay? That's not the only right answer. Okay? There's a couple of other of you gave good ideas as well. But just because I like to kind of work top down and use the upper rows to help me simplify lower rows, it makes sense to do this. And this -2 multiple is just because 2 times -2 will cancel out the 4. And then 2 times -3, sorry, -2 times -3, when I add it to -6, also becomes 0. And -2 times 1, when I add it to 2, also becomes 0. And then -2 times -1, when I add it to -3, it becomes -1. And -2 times 1, when I add it to -1, it becomes -3. And then finally, -2 times 0, when I add it to -5, it becomes -5. So I'm doing most of that math in my head. This is why you have to do this without the television on, without the dog barking, and not when you're like half asleep, right? You have to really be careful about the actual steps that you're doing here. Now, at the same time, I would like to get a 0 in the third row, and so far I haven't really worked on the third row. Can somebody suggest a good ERO that would take from this first matrix that would turn this -2 into a 0? Yeah.
Row 1, row 3.
Exactly. A 1, 3 of 1. I would just simply take the first row and add it to the third row. Because the 2 added to the -2 gives me 0. And now I just go all the way across every column. I do the same thing. -3 plus 3, that's 0. 1 plus -2, that's -1. -1 plus 2, that's 1. 1 plus -1, that's 0. And 0 plus 3, that's 3. Now I'm going to do something here, guys, that's a little premature, but it will be actually very helpful. I'm going to circle where the pivot positions would be as of this moment. So the pivots, remember, these things I'm putting diamonds around, those are the first non-zero entries of each of those rows. Agreed? Right? So as you can see, my pivots are not configured correctly because the pivots are supposed to go down and to the right. So if I wanted to get the pivots positioned correctly, what would I need to do right now? Caesar?
Permute.
Permute what?
What do I call it? With those
Which two rows?
Row 2 and row 3.
Rows 2 and 3, exactly. That would be P23. So let's do that next, guys. Let's come up here. I use this little twiddle notation to remind myself what my ERO is. I'm going to permute, guys, on rows 2 and 3. That's all I'm going to do. So I'll permute rows 2 and 3. I leave everything else the same. So 2, -3, 1, -1, 1, augmented with 0. That does not change. But now I'm going to put the third row second. So 0, 0, -1, 1, 0, 3. And then I'm going to put the second row third. So 0, 0, 0, -1, -3, -5. And now my pivots are actually compatible with the form of the row echelon form that we need. The only thing that's wrong with this matrix, as far as row echelon form goes, is that the pivots, if you remember from Tuesday, they're supposed to be 1. But now, since this is pretty much the end of the line, I don't mind just multiplying each row through by the appropriate constant to make those pivots turn into 1s. And this is something we could do them all at the same time in a single step. So I'm going to multiply row 1 by 1/2, right? I'm going to also multiply row 2 by a negative and row 3 by a negative. And these 3 operations, I don't mind doing them at one time because they kind of don't affect each other at all. So it's pretty safe to do them independently in one single step. So the first row gets multiplied by a 1/2. The second row gets multiplied by a minus sign. And the third row gets multiplied by a minus sign. So here you go. We have pivots that look like this. And that is a row echelon form for the matrix. Not the only one. As we talked about on Tuesday, the row echelon form is not unique. There can be other right answers, but this is a good one that we can now work with. And just to remind you, the unknowns in the system are the U, the V, the W, the X, and the Y, which are essentially associated with these columns. So I've done the first part of this, use EROs to bring A sharp into row echelon form. Now the rest of it is, if possible, solve it by back substitution. So we have to talk about that part because we haven't really gone over that yet. How do we now take this matrix and solve it by back substitution? Well, the idea here, guys, is this is kind of, it's almost like a triangular form where you can start from the bottom equation and then plug into the one before that, and then plug into the one before that, right? We're kind of working from the bottom back up. But if I look at just this last equation, if I go back and I write it back out as an equation again, so this third equation, there's no U, there's no V, there's no W, there's 1 X, there's 3 Ys, and it equals 5. this equation already has tons of solutions. You give me a y value, I can give you an x value. You give me a different y value, I can give you a different x value, right? There's actually infinitely many solutions here. And in fact, what I would say is that the y variable can be freely chosen. Y is a free variable from which then we could derive x. So again, if you give me a y value, I can then solve for x. The x will not be free, but the y is free. So the way we're going to write this down, guys, is y is a free variable, and I like to use R, S, and T, letters of the alphabet, to represent free variables. So you'll see me do this all semester long. Anytime I'm introducing a free variable into a system, I usually will call it R, S, and T. I do that just so that every time I see an R, an S, and a T in my work, I'm thinking, oh, that's probably a free variable. Okay, so the y is anything. You can pick any number that you want for y, but then x must be 5 minus 3y, which in terms of my free variable is 5 minus 3t. Okay, so I first have y, then I solve for x. Now, that's working on the third equation. Let's go back to the previous equation now. If I go to the equation in the middle, I have 1w and minus x equals -3. Okay, so see what I'm doing? I'm taking this matrix and I'm writing equations again for it. So notice that w is, so if I already know what x is, then w has to be whatever it is, x minus 3. Let's just solve this. W is equal to x minus 3 if I solve for w. So w is x minus 3. If I take what x was and just subtract 3 from it, well, instead of 5 minus 3t, now it would be 2 minus 3t. Okay, so again, guys, here's the game. We take any number we want for y, and that will then determine what x is, and now it will also determine what w is. Okay, and now I've still got u and v to figure out, and for that I need to use the first equation. The first equation is kind of messy. I'm going to write it down over here. U minus 3/2 v plus 1/2 w minus 1/2 x plus 1/2 y equals 0. I'm literally just taking that from the first row of my matrix. Okay. Now, we already know that y is going to be t, x is going to be 5 minus 3t, and w is going to be 2 minus 3t. That much we know. But we have u and v here. What I'd like you to notice is that the v is actually another free variable, right? Because if I know w, x, and y, that part's all determined, but I've still got these two variables here that I can play off of each other. So v is actually also free. I'm going to use an r for that one. It's a different free variable. And I like to remind myself that it's free. So remember that r, s, and t are good letters to use for free variables. Right now I'm using an r for the v variable. Now based on that, I'm going to try to figure out what u is. Okay, you guys with me? Okay, I'm going to figure out what u is. Let's solve for u. Let's just get this one. I cannot do it in my head. It's just too messy. Let's just solve for u. U is 3/2 of v minus 1/2 of w plus 1/2 of x minus 1/2 of y. So if we solve for u, that's how it would look. But I want to write it using my free variables. So where I see the v here, guys, I'm going to change that to an r. And where I see the minus 1/2 w, I'm going to replace the w with the quantity of 2 minus 3t. And then where I see the x, I'm going to replace that one with the quantity of 5 minus 3t. And then finally, minus 1/2 of y, which is just t. And so this is what you would end up with for u. And let me actually simplify that. This can be cleaned up a little bit. Let me clean this one up just a little bit, guys. This turns out to be 3/2 of r. And then if you simplify the algebra, it should be minus 1/2 of t. And then it should be plus 3/2. So hopefully I did the math right on simplifying that. That is what u is. The point is that all 5 variables, u, v, w, x, and y, have been written now in terms of the r and the t, which are the free variables. And so my solution, remember on Tuesday how we tried to get these braces to give us a good way to do the notation? We're going to write it using that notation. This is not a good way to write your final answer, guys. Just all scattered all over the place like this. We need to kind of organize it here. I'm going to make a 5-slot answer here. In the first slot, I'm going to put u, which was 3/2 of r minus 1/2 of t plus 3/2, and then comma. And the next variable is v, which should be r, and then comma. And the next variable is w, which was 2 minus 3t, comma. And then x was 5 minus 3t, and then comma. And finally, the y variable was t. And now I'll close my parentheses. So I've got 5 slots. This is the u, the v, the w, the x, and the y. And now here's some just math notation. We will usually use a colon to represent the word such that. I do want you to write this down. Such that, and then after the colon, we just want to list our free variables, which are r and t. This little E-shaped thing just means belongs to. So this is just notational language for how we write these things down. That kind of put the r and the t in the real number set. So the r and the t are real numbers. Okay. Can somebody tell me how many solutions does my system have? According to what the answer is over there. How many 5 tuples would we have that would solve that system? Say it again. Infinitely many, isn't it? It's infinitely many. Didn't I start this conversation by saying you can choose any number for y, and then I have to solve for x, and then I have to solve for w, and then I can actually also choose any number for v, and then I have to solve for u. There are infinitely many solutions since we have the real reason that there are infinitely many solutions is because there is a free variable, right? Since we have free variables. Even if you only have one free variable, it would already tell you that there's infinitely many solutions. Everybody with me? Infinitely many solutions. It's because there are free variables. By the way, as another observation, maybe I'll put a little note here. Did you notice that the free variables correspond to the columns without pivots? So the v and the y turned out to be the variables that were free. So v and y are free variables. And the point being that those are basically unpivoted. Those are the unpivoted columns in my row echelon form. The other 3 variables are the u, the w, and the x. The u and the w and the x, those are not free. If you tell me what your value for y is, then x is not free. X must satisfy this, yeah? You can almost imagine there was a pivot around that x. And then there was this pivot around this w. They are not free. And these are called, there's a name for this. These are what are called the leading variables. These are the leading variables, guys. These are the variables at sort of the front of the equations. So you can kind of just glance at your row echelon form. Every variable is either going to be a free variable or a leading variable. And the reason that you have infinitely many solutions is because there are free variables around. You wouldn't have to have free variables around. Not always, right? Let me just remind you. about that. Are there any questions so far though about this particular example? Go ahead, Brandon.
So in any matrix, whenever you have the variables that don't have any pivots on it, those will always be the free variables.
Those are always going to be the free variables. Yeah, that's exactly right. But I don't know if you guys remember our example from Tuesday. Do you remember this one? I don't even remember it. I remember doing it. I got to remember the numbers. I did an example. Here it is. 2x minus 3y plus c equals 6. And then 4y minus c equals 8. And then c equals 4. We wrote that one down on Tuesday. If we put this into an augmented matrix, guys, if we just grab these coefficients and write down the augmented matrix for this system, it would look like that. I didn't do this on Tuesday. I simply took the system and solved it by back substitution in my head, basically. But we can put it into this matrix, right? Here are my unknowns. But what you're noticing, I think, probably already, is that the positions of the pivots are like that. It's not technically quite into row echelon form yet, but it's good enough for me to know that I'm not going to have any free variables. Do you notice that all 3 variables are pivoted here? There are no free variables in this example. And you probably remember from Tuesday that when we solved this system to get the solution, we got only one solution for x, y, and z. So we had written this one down that x has to be 11 halves, y has to be 3, and z has to be 4. So there is only one solution in this problem, and it's because there are no free variables around at all. There are no free variables. Okay, so the presence of free variables dictates whether you'll have infinitely many solutions, right? Or whether you'll only have one solution. Actually, there's another scenario that can come out of all of this as well. I'd like to show you this as well. Another example. What if my system was x plus y equals 1 and x plus y equals 2? Well, you guys probably already know that this has no solutions. Okay, so this is yet another outcome. Let's just play dumb for a minute and just like go through the motions of our process and see what comes out of it. Why do we end up with no solutions? So if I just write down the augmented matrix for this, there it is. Right, and I've already got a pivot in that first row exactly the way I would want it to be. What is the ERO that I would want to do here to get this into row echelon form? A1, 2 of -1. So that would be the negative of the first row being added to the second row, right? So if I take the negative of the first row and add it to the second row, of course, it doesn't change the first row at all. But the negative of that being added to the second row actually gives me a second row of 0 and 0 and 1. And now we see what is going wrong here. Because if you look at this second row here, what does this say as an equation? It tells me that 0 times x plus 0 times y is supposed to add up to 1. That's the way you would read that equation out. And of course, this is impossible because the left side is 0 for sure. The right-hand side is not 0. So this is impossible. It's impossible to solve, which just means that there are 0 solutions. 0 solutions versus 1 solution versus infinitely many solutions on the first example. So what's causing you to get 0 solutions here, guys, is that you have a pivot in that far, far, far right column on the right side of the bar. That is a red flag, right? That is a red flag. And I'm going to write that into the notes now. So that we can write this down. Does it make sense though? Just looking at it, you know there's no solutions. How does that play out when you actually do your EROs? The way it plays out is you get this pivot in the far right column. So one of the things I want us to take away from this section of Math 250B, where we're learning about linear systems, is that, guys, when you have a linear system of equations, there are only 3 possible outcomes. Either you will have infinitely many solutions, or you will have exactly one solution, or you will have no solutions. There's no other outcome. You can't have a linear system with exactly 17 solutions. Of course, if I leave linear algebra and I go work in some other world, let me give you an equation that's not linear. There's an equation that's not linear. If I leave the world of linear algebra, the comforts of 250B, and I look at an equation that's not linear, then my statement that every equation has either 0 solutions, 1 solution, or infinitely many solutions is no longer true. And I think we all know that this equation has exactly 2 solutions, 3 and -3, right? So just be careful. As soon as you leave the friendly comforts of linear algebra, some unpredictable results can come out of it.
For the 0 solutions,
Yeah.
right away you should be able to tell, right?
Well, here we were able to tell right away. But actually, I could finagle a whole bunch of equations with a bunch of unknowns, and you might not be able to tell right away. Until you actually do the EROs, you might not be able to tell that a pivot is going to drift into that far right column. Yeah, it's not always going to be obvious. Yes, Aiden, question.
Just to reassure,
Please.
so whenever we have at least one free variable,
Yeah.
it's safe to assume that there's.
Absolutely. Absolutely. Thank you. And in fact, that's exactly what I want to write down here in the notes, guys. There are 3 outcomes of Gaussian elimination. This is worth writing it down. Actually, I even made a video. It's in my YouTube channel. If you search for a video called 3 Outcomes of Gaussian Elimination, you'll find me talking about exactly this. So what are the 3 outcomes? Let's just get this into our notes. The first one is that we could have an inconsistent system. And that just means 0 solutions. Inconsistent just means 0 solutions. And how does that arise? Well, the way that plays out in your work is that you get a pivot in the far right column. So you would get a pivot into that far right column. So that's what happened right here in this last example that we just did. So if you do your EROs and a pivot is over in that right side of the bar, that's an inconsistent system, no solution. The second outcome is going to be consistent with no free variables. It could be consistent, but with no free variables. This would be the case of exactly one solution. So I'll just say one solution in that case. And again, if you need an example that models that, this one here at the top of my board on the left shows exactly how that would look. In this example, the pivots did not make it into the far right column, but there was no free variables. Every variable was a leading variable, right? Every variable was pivoted, in other words, okay? And then the last case, number 3, guys, it could be consistent with free variables. And that was the very first example we did, and that's the case of infinitely many solutions. That's the case where you get infinitely many solutions to your system. Okay, so that's kind of what you want to be on the lookout for. It's so critical. It's so critical to focus on the positions of the pivots, right? Because the pivots are dictating whether you have free variables or not, right? And so that very much affects the outcomes here. Okay, I'd like to do one more example that actually kind of captures all three of these outcomes in one single problem. And I'll show you what I mean by that. Let's put it over here, and then I think we'll call this good. So consider the system. I'm going to make an example now, guys, and let's write it down. Here's my system, x plus 2y minus c equals 3. And then the second equation is going to be 2x plus 5y plus z is equal to 7. And then the third one is going to be x plus y minus, now here's the funky part, guys, k squared times y, times z equals negative k. So what is this k business about? Well, it's some value, and I would like to determine which values of k give the three outcomes above. So that's the way I want to work this problem. I'm going to actually try to figure out, okay, so for what values of k do I get no solutions? For what values of k do I get one solution? And for what values of k do I get infinitely many solutions? Okay, so let's just see if we can do that as a little practice. I'm going to just set this thing up as an augmented matrix, and the fact that there's a k in it, I'm not going to flinch. I'm just going to go like normal and write this down. Okay, so just check this out. Yeah, question.
So that's something you would always want to do when we're doing like the EROs, always set it up as an augmented matrix.
Augmented matrix is always step one. Yes, absolutely. So the very first thing right here, guys, is we're going to write down the A sharp right here. So I go across, the first equation is a 1 and a 2 and a negative 1 augmented with 3. And the second one is a 2 and a 5 and a 1 augmented with 7. And then a 1 and a 1 and a negative k squared augmented with negative k. So I'm just going ahead, I'm leaving the k in the matrix that I've written down here. Okay, so let's bring this over here. So there's your augmented matrix. So far, so good. Now, the first row, I can see already I've got a pivot exactly in the upper left corner. I'll go ahead and circle that one because I'm happy with that. Would somebody like to suggest any ERO that we could start off with here?
Multiply by -2 and add it to the second row.
Okay, so that's adding with rows 1 and 2 of a -2. So I'm just looking at these two numbers. How can I turn this 2 into a 0? By using the first row, I take -2 times the first row and add it to the second row. This is the notation. We learned this on Tuesday, right? So -2 times the first row, add it to the second row. The first row stays the same. So notice the first row does not change when I do that. For the second row, I'm going to get a 0 there. Okay? And -2 times 2, when I add that to 5, it's 1. -2 times -1, when I add that to 1, it's 3. -2 times 3, when I add that to 7, I get 1. And I'm going to go ahead and circle a pivot. I already created a pivot right there. Is there another good ERO that I could do at the same time right now, guys? With the third row, and what ERO would that be? What would be the notation for that ERO that I'm going to use? A 1,3 of -1, right? I'm just looking at these two numbers. I want to use this 1 to cancel out this one. So negative of the first row added to the third row will put a 0 here. That's all I care about, guys. I'm not even looking at the rest of the matrix. I'm just saying, how do I get a 0 right there?
You just want to get the first column essentially.
Yes, you want to get this first column to be 1, 0, 0. Right. So I take the negative of the first row and I add it to the last row. So I'll get 0, and then I'll get -1, then I'll get 1 minus k squared, and then I'll get negative k minus 3. Just like that. Okay, so now I need another ERO here, guys. Because it's not in row echelon form yet. Can somebody suggest a good way? So remember, below every single pivot, you must have 0. How can I turn this -1 into a 0? Aiden.
Add row 2 and 1. I'm sorry, 2 and 3.
Add row 2 to row 3, which would be 1 times the second row added to the third row. Exactly right. So the first row does not change. The second row does not change. It's only the third row that's going to be affected by this. And when I add the second row to the third row, I'll have 0, and then I'll have 0, and then I'll have 4 minus k squared, and then I'll have negative k minus 2. So be careful, I'm just adding the second row to the third row, and I still have this k parameter that's kind of with me through that calculation. Okay. We're getting in pretty good shape here. The columns are aligned with my unknowns, which are the x, the y, and the z. So again, these outcomes over here are very dependent on pivots and free variables. I see 2 pivots already. A question I would have for you right now is, do I have a pivot in the third row? Or, I mean, will I have a pivot in the third row? The answer is, it all depends on what k is, right? Would you guys agree that as long as k does not equal 2 or -2, as long as k does not equal 2 or -2, then I would have a pivot position right there in the third row. If k does not equal, let's write this down. If k does not equal ±2, this is going to be not 0. This will be not 0. And if this is not 0 right here, guys, then it can be made into a pivot. It would become a pivot, yeah? And if that was a pivot, if it was a pivot, how many solutions would you have? No solutions, 1 solution, or infinitely many?
1 solution.
It would be 1 solution. It would be, if this was a pivot, guys, if this was a pivot, then I don't have a pivot in the far right column, but I also don't have any free variables. So in this case that we're kind of talking about here, if k does not equal ±2, we have 1 solution.
And for whatever reason, if it was ±2, then we'd have infinite, right?
Well, I'm going to talk about both of those scenarios next. So it is possible that k could equal 2 or -2. Let's talk about it. If k is equal to 2, then when I read this bottom row, in this case, the bottom row, I'll just put it here, is 0, 0, 0, augmented with -4. Right? So if k equals -2, oh, I'm sorry. No, I did that wrong. If k equals 2.
Yeah, it's right.
Oh, I did it right. Second guessing myself. So if k equals 2, then I have 0, 0, 0, and -4. And of course, this is where the pivot would really reside. How many solutions is that? No solutions. Pivot in the far right column means no solutions. So we have, in this case, 0 solutions. Nice, okay? The other possibility is, well, what if k was equal to -2? If k was equal to -2, how would this bottom row actually look? Well, we would have a 0, another 0, and another 0. actually. If k was equal to -2, this last row is just all zeros. If that last row was all zeros, then you don't really have any pivots. You just have all zeros here. How many solutions does this have? Infinitely many, doesn't it? Right? Because there's a free variable now. The free variable being z, right? In that case. So in this case, we have infinitely many solutions. Does that seem okay? Making sense? Yeah, okay. Now let's just carry out the solution in this third case. I'd just like to practice one last time with you. So in this case, if this third row is all zeros, then that's really a wasted row and there's no information there. I can kind of just wipe it out. But I do see that my z variable is free. So let's just come over here and write down the z is free because there's no pivot on the z variable. Going back to the second row, I see that y plus 3z is equal to 1. Y plus 3, this is c right here. Y plus 3z is equal to 1. So if z was equal to t, then y would have been 1 minus 3t. Solving for y, we would get 1 minus 3z, but that becomes 1 minus 3t. And now I have to go back to the first equation to solve for x. The first equation is x plus 2y minus c equals 3. So I'm going to solve for x now, right? So if I solve this for x, I'll just do it right here. It's going to be 3 minus 2y plus z. Don't let me go too fast if you're not clear. This is the part sometimes people get a little bit scared of. We're just rearranging this equation to isolate x. So x would be 3 minus 2y plus c. And now I just have to feed in what y is. So it's 3 minus 2 times the quantity of 1 minus 3t plus z, which is itself t. And if we clean this up, just simplify the math of this, it looks to me like we get 1 plus 7t. Am I doing that right? Check me on that. 1 plus 7t. That should work.
That z equals t free. Was that
T is
from the
free.
Oh, okay.
Yeah.
I wasn't sure if that was from the
It's
previous problem.
it's unpivoted in this third column now, so that's always a free variable. Yeah, exactly. So am I going to leave my answer like that?
No, you gotta put in nice notation.
I got my nice notation. Yeah, I'm going to make my set notation for this. So I'll write down my answer, the set of 1 plus 7t, comma, 1 minus 3t, comma, t. This time we have just those 3 slots. So we put the x, make sure you do them in the right order. X goes first, y goes second, and z goes third. Then I'm going to use my little colon with the such that. And then this time, t belongs to, or is an element of, the real numbers. And this would be your answer. This would then be the answer in that case. Okay? By the way, you should be able to check that answer. Like if you came back to any one of the equations from your original system and you plugged in the x, the y, and the z. So like on the first one, you actually had to do this on the homework that you turned in, I think, already on Tuesday. So you just verify it. The x was 1 plus 7t, and then plus 2 times the y, which is 1 minus 3t, and then minus z. So I just take this first equation just to check it. If we add all of that up, we should get 3. And we do. All of the t terms cancel, and you just get 3. So it checks out there. And if you similarly plug into the other ones, they should also check out. So it is possible, of course, to check these answers. What do you guys think? Making sense? Pretty good? Okay, fantastic. All right. Any questions about this Gaussian elimination? Isaac?
So I understand how the leading variables appear, but can you define what characteristics makes them? Is there anything besides the pivots?
It's really because they are pivoted variables that they are the leading variables.
So is it because they have their variables with a coefficient of 1?
They have a coefficient of 1. They're always on to the left because remember the pivot is the first non-zero entry in any given row. So you're seeing the pivots circled here on the left side. Now, guys, some of you might have a question for me. And I've seen people do this and it always drives me nuts. You get this equation here, y plus 3z equals 1. And I've seen people do this. I've seen people say, oh, I'm actually going to solve it for z instead. Now, that's not wrong. This is absolutely correct. But if you start doing stuff like this, you're actually not taking advantage of this whole very structured framework of putting the variables from left to right, getting the matrix into row echelon form, and solving it out. If you start doing stuff like this, what you're sort of saying to your professor is, I'm going to do this the same way I could have done it in high school. Right? We could have messed around with this even in a high school math class. Just, oh, let's solve for z in the first equation and then plug that into the second one, and then we'll get the x and the y combined together and just like mess around with the equations. Okay, we all would have been able to do that like years ago, probably, right? The whole purpose here, guys, I'm trying to give you like a perfect structure, where it's like, okay, if you just follow the Gaussian elimination process, write down your A sharp, do your EROs, circle your pivots, establish free variables as the unpivoted ones, and go backwards through your matrix, you'll get it right every time, and you won't get so tangled up in a confusing circle of algebra, right? So this will keep you from ever having that problem. So,
Just really quick.
yeah.
After you get those two, can you just do a quick recap of after you get those two equations?
These two, yeah.
Yeah.
Mhm.
Where do you go from there?
I start on the bottom because
Yeah.
it's back substitution. So you're going backwards through your work. From the bottom equation, I identify, if I want, I could even put pivots here. I identify that my free variable is C.
Right.
So I call it T right off the bat, and I just solve for my leading variable in terms of the free variable. So that's what I did for Y. Then you take all of that information and plug it into the previous equation and solve for the pivot that's in that equation.
Okay.
Yeah, that's kind of the systematic approach. Yeah, go ahead, Oscar.
And the reason why z is a free variable is because there's a zero on the last. So
It has no
It's
pivot.
because there's no pivot in this third column, right? And that is because this was a zero. Yeah. Great point. I love these questions, guys. This is really, really good. We're going to move on a little bit from this. Obviously, we have a lot more to do, but this is going to keep coming up. Like, we're going to need to keep using it. So this is a great time to really try to get this down. So for tomorrow's homework, you'll get some practice with this. I think in the homework, you'll see all three cases showing up somewhere. So you'll get a chance to make sure you're on top of it. And I really hope you will ask me in my office hours if you've got questions as you start working those out.
But this is like generally like from this section what we have to like master, right?
Oh yeah. This is I don't teach anything that you don't that's not really the mainstream stuff. I'm focusing on the mainstream stuff here. Okay, I'm gonna talk just a few more minutes, then we'll take a short break. I want to go back to something I mentioned on Tuesday, switching gears just a little bit, and I want to talk about something in the next section real quick. Section 2.6, I don't know if you remember, I mentioned on Tuesday that you can also write your linear system in a matrix equation form like this. And I mentioned, we would love to solve for our unknowns, which are the x vector. And to do that, from this perspective, you might be thinking about dividing by a. And of course, when I went over the properties of matrices, we had a lot of them, but we never said anything about dividing by a matrix. I'd like to see if we can make some kind of semi-pseudo approach that would be like dividing by a matrix. And that is what this section is about. It's called the inverse of a matrix. So I'm just gonna start this for just a few minutes before we take a short break, okay, just to at least get the stage set up. So let me start with a definition. I want to define what the inverse of a matrix is. The first thing is we have to let A be an n by n matrix. Now, I don't know if you realize it, guys, but that is already a huge constraint. If your matrix is not a square size, like on that very first warm-up problem we did today at the beginning, then this whole section does not even apply. We can't even use what I'm going to talk about. So it has to be a square size matrix to begin with. So if there is another, I'll just say an n by n matrix B with A times B equaling to the identity matrix equaling to B times A, then we say B is an inverse of A, and A is invertible. A is invertible. Huge important word in linear algebra, in the theory of matrices. So a square matrix might be invertible if I can find another square matrix of the same size, such that when I multiply them together, I get this identity matrix. Let me just remind you guys over here, the identity matrix, this was in the video over the weekend, and we talked about it briefly on Tuesday. This is just a matrix that has all ones on that main diagonal of the matrix and zeros everywhere else. That's the identity matrix. And this matrix is like a 1. It isn't literally the number 1, but it plays the same way that the number 1 does. If I take 1 times anything, it doesn't change what I have. The identity matrix is just like that. If you take this identity matrix and you multiply it by anything, it just leaves that other matrix as is. It leaves it alone, right? So this is the definition. I'm going to ask a quick question here about this definition before we go any further. And the question that I want to ask is, can an invertible matrix have 2 inverses? Could there be 2 of them? And it might feel like this is a pretty advanced type of question to be asking. We haven't even done an example yet. But actually, we can answer this one right away. It's very easy from a theoretical perspective to answer it. The answer is no. A matrix cannot have 2 inverses. I would actually like to show you a little calculation that proves that. It's going to be like a proof. Can I do a proof? Is that okay, Stephen? Sorry?
Can you slow down a little?
Yeah, I get excited. Do you have a question? Okay. So the answer here is no. An invertible matrix cannot have 2 inverses. And the way you would justify that is by supposing that there are 2 inverses and then show that they're actually the same. So let's do that. Let's suppose, so here's, I'm going to give you a proof here of this conclusion. All right. So suppose B and C are both inverses of A. Suppose we actually have 2 inverses for A. So let's call them B and C. I'm going to try to convince you that B has to be equal to C. They cannot be 2 different inverses. B actually has to be equal to C. Let me show you that, guys. So we have AB equals the identity equals BA. And similarly, AC is equal to the identity is equal to CA. That's just the definition of inverse, right? So a matrix is an inverse of A if when you multiply by it on either side, you get the identity matrix. So if both B and C are inverses of A, all of this would be true. And so then I'm going to try to show you that B is equal to C. Watch this. This is really cool. B, ready? So it's a one-liner, guys. It's a one line. B, I don't think anybody could argue with me that if I multiply by the identity matrix, nothing happens. Remember, that's like multiplying by 1. I can put that identity matrix in there. And the identity matrix, I'm now going to replace that with AC. Notice that A times C was the identity matrix, so I'm going to just feed that in there. And now I'm going to remember from our properties of matrix algebra, I cannot switch the order of anything, but remember from Tuesday that parentheses actually don't matter. I can switch the way the parentheses are written down. So I'll put the parentheses with the BA. What is B times A? The identity matrix says it up here at the top. Identity matrix times C. And what's the identity times C? Just C. It's like multiplying by 1. It's just C. Look at that. B is equal to C. So there is only one inverse
Could you,
for a matrix.
could you like restate it again?
Restate what?
The
This whole thing is what it is. So starting with, if I assume, so the way people prove that there's only one unique inverse is they suppose there's 2 of them. Call them B and C. That at the beginning of the conversation, they have nothing to do with each other. I'm just imagining I have these 2 different inverses. And then I'm just going to show you that B equals C. And this is just the baby steps of using the definition of inverses to make that proof work. So it's very, very short. These theoretical proofs are usually very, very short. But the point is that there is only one inverse for a matrix. So as a notational point, I'll add this here. If A is invertible, in that case, the inverse of A is written as A to the -1 power. So I'm not going to be writing the B and the C any longer. As soon as I realize there's only one inverse for A, I can write it as an A to the -1 exponent. Okay? So there is only one inverse for A. Why did I start off with this question first? Why did I want to ask whether there could be 2 inverses first? Was because I wanted to get this notation. If I wrote this notation in the beginning, it might be not clear that there could only be one answer. As soon as there's only one answer for the inverse of A, I'm really happy to use this notation to write it down. It's just a handy notation to have. So with that in mind, now I want to give you an application of this. I've already talked about it, but I'd actually like to write it down. And then we'll take a little break before we actually, and there's other questions you probably are going to ask me is, how do you find the inverse? How do you know if there is an inverse? And of course, this one, who cares? Right, what's the application? So those are the obvious questions to ask here. And the application is one that I've already mentioned. So if you have this n by n matrix A, and you're looking at A times X equals B, right? So if that is the case and A is invertible, if A is invertible, meaning that this inverse exists, and we can write it down, then I can take this linear system. This is just my linear system of equations, right? Just my linear system of equations. I can take that linear system and I can multiply by A inverse on the left of both sides of the equal sign. So I take my original problem and I'm just assuming I have an inverse for A and I know how to find it, which of course I still have to explain later. But assuming I can do that, I can put that A inverse on the left of both sides. What is A inverse times A equal to? The identity matrix, right, exactly, because see, this definition here says that the inverse for A, when you multiply A by its inverse, you just get the identity matrix. So guys, this is just the identity matrix times X equals A inverse times B. And the identity matrix is like the number 1. When I multiply 1 times anything, it doesn't change what I have there, which is in this case just X. So I'll stop and take a breath here. That's the conclusion. Given, I mean, this is what we wanted. This is what the 10-year-old would have told us to do. 10x equals 7. I want to solve for x. I take the inverse of 10 and multiply by 7. So you just, it's like dividing by A, right? You're basically saying, I want to move the A to the other side of the equation. Now, we're not literally dividing by the matrix, but we've now found something that sort of gets the job done, which is to isolate the x by moving A inverse to the other side of the equation. Yeah, so this is effectively, we have divided by the matrix A. That's assuming that A is invertible, and it's assuming we know how to find the inverse, which I haven't explained yet. Yeah, question?
Because inverse A times B is supposed to equal 1, does it matter what direction or what side it's on?
No, A inverse times B is not equal to 1, my friend. What it is A inverse times A is equal to the identity. And for that, it is true that you can put it in either order. Yeah. Over here, yeah, we need to keep, this is an n by n matrix and this is an n by 1 column, and it's got to be in that order.
Okay.
Yeah, good point. Okay, so let's just write down the 2 questions I keep talking about, and then we will take a break, and then we'll kind of answer those questions. But let's just get the questions written down first so that I've got them on the board for us. So the natural questions. The first one is how to decide if A, which is n by n, is invertible. That's question number 1. How do we decide if a matrix is invertible? And secondly, if so, if it is invertible, how do we find that inverse matrix? Those are the 2 questions of the hour that we definitely need to talk more about. So, but let's take a break first. We've been talking for a little while. Take 10 minutes, get some fresh air, catch up on your phone, water, whatever you need. Go run around the building 10 times. Doesn't matter to me. But at about, they fixed my clock. At about 20 after 10, I will start answering those questions. Okay, we'll take a short break. Yeah. Oh, no. I just wanted to see the technical.
There was some more before. Okay, then I will have to check. Okay, for sure, no problem.
Dale. No, I did not do a sign. Oh, you did a ten. I did it on Tuesday. I think you were here Tuesday, right? Yeah, so, but I normally take attendance every day, all the time. But, I'm still, there's still a few people who are trying to add the class, so when people have been missing, I've been sending emails out to them because I just want to see who are you really coming or not. If not, I'm gonna let you know. So, yeah, that's all. Okay, perfect. Yeah.
That's not what. Or like. No. I have this is a new professor. He made a study guide exactly like when you test. Actually, I was just.
It's not considered a contradiction. Let's suppose that there's not just one inverse for a matrix. So then we imagine that there's two, and we find out that that's actually impossible. So the end of the proof is that, B is equal to C. So that more or less contradicts the fact that they're doing more than one. I probably should have written one more sentence. But yeah, that's it.
It's almost hard enough.
Right. Preference. I'm not a morning person. It's too dark, I'll fall asleep.
I was gonna mention that this right here, where you're talking about the inverse system, it kind of reminds me of like launch gates.
Yeah.
Cause like,
I
I don't know if you're familiar with that.
I am very familiar with that. I cannot disagree with you.
I can see it, I'm like, it's like,
It's there. Well, I guess we've got just about everybody back. Does anybody want to ask me any questions about either this sort of this proof that an invertible matrix cannot have two inverses, or this application? Keep in mind, when I write this application down, if this is your linear system, you don't have to do any of this material I'm talking about right now. You can always just go back to the A sharp again, which is what we're doing in the first part of our class today. Just write down your augmented matrix, and you want to solve for X? No problem. We learned how to do the Gaussian elimination, right? Do the EROs, bring the matrix into row echelon form, and solve it by back substitution using free variables if necessary, right? So I'm not trying to say that the stuff we learned previously isn't still critical. I'm just saying that I'm about to explain for you another way to solve for X if the A is invertible. Yeah, Brandon?
On like say the experiment.
Okay.
Like, oh, you have to do it with the inverse.
I'm usually not that type of a test writer. I don't usually like say, oh, you have to do it my way or you have to do it this way. It'll be more open for you to think about. If I really don't want you to use the inverse way, instead of telling you don't use the inverse way that you're learning right here, I would probably just make a problem where A was not invertible. And then this is only going to work, right, guys? This only works if A has an inverse. That's the only way I can solve for X here. The A inverse even shows up in the formula. So you're not going to use this method all the time, only when the matrix is invertible. And we haven't even talked about how do I know if it's invertible and how do I find the inverse? These are the questions the burning questions that we have to answer. So I'm going to answer them for you, hopefully in this next rest of our class today. Turns out that to answer these questions, it's easiest for me to answer them when n is equal to 2, first of all. So I'm going to start off with just a 2 by 2 scenario first. When n is equal to 2, guys, your matrix is literally just going to have 2 rows and 2 columns, and I can write it out with all the entries just labeled as A and B and C and D. Okay, so the first row is A and B, second row is C and D. When the matrix is only 2 by 2, I can answer these questions very easily. So the answer for number 1 is very easy. A is invertible if and only if, so I'm going to give you a perfect way to check it, and it's super easy. AD minus BC is not equal to 0. So that's the formula. That's the formula. And so the easy way to remember it is you multiply the 2 diagonal values, and then you multiply the other 2 values, and they shouldn't be the same. Is it too bright now? You can put it back down. So during the break, it's too dark. So if that's too much sun coming in, just feel free to drop that shade back down. Sorry about that. Okay, so in the case when AD minus BC is not equal to 0, A will be invertible. And then the question would then be, well, what is the formula for the inverse? I'm going to give it to you. This is one formula that really is worth memorizing. This one will be worth memorizing. And it is the following. You take 1 over AD minus BC, okay? And then you build out your 2x2 inverse in the following way. So this is what you need to memorize. You swap the A and the D. So you put the D in the upper left and the A in the lower right. So you swap the A and the D. And then on the B and the C, you just do a sign change, but you leave them where they were. Okay, so that is the formula for the inverse of a 2x2 matrix. You swap the A and the D, you do sign changes on the B and the C, and then out in front, this is a scalar multiplication here. This is just some number out in front. And notice that this number is not 0. So we're not dividing by 0 here. By the way, if you were doubting this formula, if you were not convinced, maybe I'm lying to you or something, how would you be able to check that this is correct? Are you just going to believe me? Or is there something that we could check? How could we check that this right here, this matrix right here, is the inverse of this matrix right here? How could we check that? What's a way to verify that? What is a way to verify that two matrices are inverses of each other? Yes, Joel. By multiplying them together, right? Because what do we know? If we multiply a matrix by its inverse, we should get the identity matrix. Let's check that. Let's take the A inverse. Let's take the A inverse and multiply it by the A. And I'm just going to show you the math of that real quick. I'm just going to work it out. A inverse is 1 over AD minus BC. Sorry, guys. It just got sunny right when I put those up. 1 over AD minus BC, and then we have a D and a negative B, and then a negative C and an A. And then that's being multiplied by the original matrix A, which is A and B and C and D. Okay? So we're going to just check that if we take A inverse times A, that we hopefully get the identity matrix. Let's just check it out. Okay? So I've got 1 over AD minus BC. And now I have a 2x2 matrix times a 2x2 matrix. So everybody has to remember how to do this dot product matrix multiplication process to get the results here. So if I'm in the upper left corner, I take the dot product of the first row with the first column. And as you can see, that's AD minus BC. AD minus BC. What about on the top right corner? Well, now I have to dot product the first row with the second column. And this is BD minus BD. That's 0. BD minus BD. All right, let's go to the bottom row of the matrix. Let's take the bottom row of negative C and A, and let's dot it with A and C. So that's negative AC plus AC. That would be 0. And then in the bottom right corner, I have negative BC plus AD. In other words, AD minus BC again. That's the results of the matrix multiplication. And this scalar multiplication, this 1 over AD minus BC, I can throw it inside all of the slots of the matrix. I can just multiply it through. And I need just a little bit more room here. But what happens when you basically move this scalar into the entries is you get 1 and 0 and 0 and 1. And that is your identity matrix. This is I sub 2. It's my 2 by 2 identity matrix. It's just, it follows this format right here. This was my general identity matrix. So that kind of checks it. That kind of checks it. So guys, anytime you want to show that two matrices are inverses of each other, you can simply multiply them together using matrix multiplication and just confirm that you get the identity matrix back. That's the process, and you are going to see that come up. It's definitely one that to be comfortable with. Okay, so far so good. So I'm not even going to do an example right now because this is really very easy. If I give you a 2 by 2 matrix like this, you can write down the inverse just by putting the right numbers in the right places. So we'll move on. The harder question is, what about bigger matrices? This was the answer for n equal to 2. For larger matrices, the bad news is that I don't have a nice simple formula for the inverse of it. Instead, what we're going to have to settle with is a process to get it. There will be a process for finding the inverse of a larger matrix. I can't just give you a one-size-fits-all formula for the inverse of, say, a 3 by 3 or a 4 by 4 or a 5 by 5 matrix, right? We have to actually have a process. So let's talk about that process a little bit. So what if n is greater than or equal to 3? We've answered the two questions when n is 2, which is actually the most important case. But what if n is greater than or equal to 3? Well, we need a new concept for that. And so there's, like I said, there's no simple formula for this. I have to give you a little bit of a process. And so I'm going to make a definition to help me with this. Make a quick definition here, guys. And it's the definition of something that's called an elementary matrix. So an elementary matrix is obtained. What is an elementary matrix? It is just a matrix that is obtained by applying one ERO to the identity matrix. So an elementary matrix is just, okay, you started with the identity matrix and you just did one ERO to it. Let me write down a couple of examples of elementary matrices for you, just so you have some to look at. So here's an example. I usually like to use E for the elementary matrix. This one will be E1. So let's take this matrix, guys, 1, 0, 0, 0, 0, 1, and 0, 1, 0. Now, keeping in mind that the identity matrix for I3, the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Can somebody explain to me what ERO would you be doing that would then give you this matrix? Brandon? Exactly. So this would come from doing P23. Right? So you would be permuting rows 2 and 3 of your identity matrix to get this one. Pretty easy. Let me write down one more example. Suppose I gave you E2. E2 might be 1 and 0 and 7 and 1. I'll just make a little 2 by 2 example here. So again, if I started with my 2 by 2 identity matrix and I wanted to turn it into this matrix, what ERO could I apply here that would then create that matrix? Go ahead, Aidan.
-7 times row 1 plus row 2.
Okay, so it's the A operation, A1, 2 of 7, right? So those notations are really important. If I take 7 times the first row and then add that in my head to the second row, I get this. So this is another example of an elementary matrix. It's just a matrix that is obtained by doing one ERO to the identity matrix. And an interesting observation is that, I'll just maybe call this a remark. Leave a little bit of space over here, guys, on the right side of those notes, because maybe go down in your notes a little bit, because I want to come back and put something over there in a second. But let me make the remark first, and then I'll show you the remark in that little white space that I left there. And the remark is that left multiplying a matrix by an elementary matrix if we left multiply a matrix by an elementary matrix, it has the effect of performing the associated ERO. It has the effect of performing the associated ERO. So I like to show you what I mean. If I take this, this is where I wanted to have this white space here. If I take this elementary matrix that I just wrote down in this first example, and I left multiply that matrix onto any other matrix, let's just say A, B, C, D, E, F, G, H, I. So if I take any 3x3 matrix and I left multiply it by this elementary matrix, look at what happens when you actually calculate it. When we actually do our matrix multiplication process to fill out this result, right? I go across the rows of the first matrix and I dot those with the columns of the second matrix. What are we going to get here, guys? In the upper left corner, A plus 0 plus 0. That would be A. And then B plus 0 plus 0, which is B. C plus 0 plus 0, which is C. On the second row, 0 plus 0 plus G. And then 0 plus 0 plus H. And then 0 plus 0 plus I. And now on the third row, 0 plus D plus 0. And then 0 plus E plus 0. And 0 plus F plus 0. Look what happened. Look what happened. The associated ERO that created this elementary matrix effectively is what happened here. The second and third rows of this random matrix got switched. They got switched, right? So that's my point. That's what this remark is saying. If I do it on this example, take 1071 and I multiply that by a random ABCD. Okay, we can do that super easy, right? Just do the matrix multiplication. A plus 0 is A, B plus 0 is B, right? On the first row. If I go to the second row, 7A plus C. And then 7B plus D. This result here, guys, is the effect of doing A12 of 7 onto this matrix. Adding 7 times the first row to the second row, you see the second row has been changed according to that ERO. You guys actually don't look all that excited, but what I've really shown here is that we can encode the EROs as matrix multiplications. So instead of just like saying in our heads, okay, I'm going to add 7 times the first row to the second row, we don't have to just say that in words anymore. Now, if I want to add 7 times the first row to the second row, I can do a matrix multiplication that has that effect. And this is it. This is it. If I take this elementary matrix and multiply it by anything, the effect will be that that ERO, in this case A12 of 7, will be applied onto that random matrix. That's pretty neat. So we can actually do that. what does this have to do with finding A inverse? That, I've got to get to that stuff. I haven't really talked about that. This is the concept that we're gonna need.
So by you multiplying it by the A, B, C, D, to whatever matrix you have,
Yeah,
that's doing the operations of the EROs.
yeah, yeah, that's my point. My point is that these matrix multiplications have the same effect as performing the associated ERO did.
By doing that, you think it's more efficient?
Not necessarily,
Not really.
but notationally, for what I'm about to go over, it'll be very helpful to express all of this using matrix multiplications. Yeah, you'll see, you'll see. So let me make another quick definition here, guys, and then we will get to the process for finding the inverse of any matrix. I gotta get this done in 10 minutes. I think I can. So we say that A is row equivalent to B. A is row equivalent to B, and this is going to be written, the notation I like to use, guys, I write A, and I put a little arrow with the word row on it to B. A is row equivalent to B if there exists elementary matrices I'm going to call them E1 and E2 and E3. I'm going to say dot, dot, dot. Maybe there's a K of them. So all the way up to E sub K with the following equation. Starting from A, I left multiply it by E1, and then I left multiply that by E2, and so on until I get all the way to E sub K, and then it equals B. Just so everybody understands, I'm not saying anything terribly heavy here. All I'm saying is that if we start with a matrix A and we left multiply by E1, i.e. we perform an ERO, right? So if I take a matrix and I perform an ERO, and then I perform another ERO, and then I perform another ERO, and so on, however many times I want to do it, whatever I'm getting as a result of any of those processes, any of those steps, is just a matrix that's row equivalent to the original matrix. So if you guys go home and you do the homework for tomorrow, where you have a matrix A and it says find the row echelon form of A, every single matrix that's written down on that paper from start to finish is just another matrix that's row equivalent to A. Because after all, you started with A and you hit it with EROs. That's really what this left side is saying. Start with A and hit it with an ERO, then hit it with another ERO, hit it with another ERO. These elementary matrices have the effect of performing the associated ERO. We sort of showed two examples of that here. So that's all that you really need to know.
But
And in fact, yeah, go ahead.
you know how we get the matrices with EROs? By you multiplying it by like that A, B, C, D.
Yeah, that's just a random matrix there that I've written down.
By multiply by another matrix, that's only performing one ERO, right? Or is it performing all of them?
This is only one ERO. So this is E1 times A, basically.
Is there a way to do it so that it performs all of them?
Well, you have to, in succession, perform one operation at a time. And that's denoted as all of these E's being piled up.
I just thought maybe like there was a way that you could do them all at the same time. But
Not really.
okay.
No, you have to do it step by step.
Right.
If we could do them all at the same time, we would immediately write down the row echelon form of a matrix without doing any work. Because you just start with your matrix and write down the row echelon form. No, we have to write it all out step by step. So as a quick note, and then we're going to get to the answer to those two questions that I just erased. If A happens to be row equivalent to the identity matrix, Okay, so what does that mean? That means I started with A and I hit it with a bunch of EROs and I ended up getting the identity matrix. So we have, in this case, we would have EK times dot, 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 times E2 times E1 times A equals the identity matrix. So does everybody see? All I'm saying is, so the definition of A being row equivalent to B is that I get, sorry, I'm circling the wrong thing. A being row equivalent to B just means this, guys. So all I'm doing is I'm saying, well, if A happened to be row equivalent to the identity, by the way, that says if. Not every matrix will be, right? But if A is row equivalent to the identity, then this equation would be true. And if this equation is true, then does everybody see that this matrix A would be invertible in this case? Let me add that here. The A inverse does exist in this case. Do you see what it is?
The E's.
The E's all multiplied together, right? Remember, what is an inverse for a matrix? It's some other matrix that you multiply it by to get the identity matrix, right? Everybody remember this? A inverse times A is equal to the identity matrix. So whatever A is being multiplied by, in this case, all of these E's, is your inverse of A. Okay? So the A inverse is this part right here. It is that part right there. That is exactly right. Okay? Now, before you panic and think, oh gosh, we're going to have to do K matrix multiplications or something and figure out all of these E matrices, it's much easier than that. And I'll show you right now. There's a name for this method, and it's called the Gauss-Jordan method. So I'm going to show it to you here. So this is called, last thing for today, guys, the Gauss-Jordan method.
Who, do you know who that, who is that guy?
Let me get back to that later. I'm running out of time. Just want to get this method down, and then we'll take some questions. So the Gauss-Jordan method is a procedure for finding the inverse of A. And it just comes in 2 steps, okay? The first step, here's how you're going to do it, guys. You're going to form the n by 2n matrix where you put your matrix A on the left side of it. Now that matrix is n by n. And you're going to sort of create an augmented matrix, but this time the augmenting is an entire identity matrix. So what you've really got here is you've got an n by n matrix kind of on the left half, and you've got an n by n matrix on the right half. Okay? So how do you find A inverse by this method? Well, what you do is you simply apply, step 2, you simply apply EROs to the entire block of this n by 2n matrix. So what I mean is you'll have A on one side, the identity matrix on the other side. Now, when I perform an ERO, guys, what I'm doing is I'm multiplying by an elementary matrix. So the first operation might be E1. That's an elementary matrix. That's a ERO that's being encoded as a matrix multiplication. Right? So that's E1 times A augmented with E1. And then the next one, there's another ERO, let's say E2. So we apply E2 all the way through the entire block. Okay? And we keep going like that, my friends. We just keep applying EROs. Eventually we'll get EK, dot, 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 to E2, E1, and A, augmented with EK, dot, 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 E2, E1. Now, what is EK times dot 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 times E2 times E1 times A?
The inverse
It is
identity matrix.
the one on the left that has the A on it is actually this one, which is the identity matrix, right? This is the identity matrix. At the very moment that the identity matrix is showing up on the left side, what is showing up on the right side?
The inverse.
The inverse of A. Yes, that's exactly right. This is the A inverse. This is the procedure. This is the procedure. We put A on the left side and the identity matrix on the right side, and we do EROs through the whole thing until we get the identity matrix on the left side. And at the moment we achieve that, our inverse of A will be on the right side. Now, there's a catch, which is that maybe you were never able to get the identity matrix on the left side. Maybe it's never going to happen. Your EROs all day long never are able to create the identity matrix on the left side. If you cannot do this, if you cannot follow step 2 all the way to this last step, what does it tell you? Sorry? That A is not invertible, that the matrix that you were given, that you started with, does not have an inverse, right? So I say this is the 2-step process for finding A inverse, if possible, if it exists. And it's all just EROs here, okay? I think I'm gonna make a little 5-minute video with one example of this for you to watch over the weekend, just so you can see how it works. It's just totally crunching numbers and doing EROs. I think I'll do that so you don't have to wait 5 days to see me give you an example of it, but it'll be a quick little video, I promise. All right, guys, that's all I've got time for right now. Thank you for being here. I'll be going downstairs for a bit if you've got questions. And I wish you a wonderful Super Bowl weekend. I will be out doing all of my errands during the Super Bowl. I don't even know who's playing in the Super Bowl.
Seattle and